because it's just a unless you go to a very high frequency.
Yeah, why not? But it's still, it's always probability on the edges. Never
Unless we're in a harmonic oscillator.
That's true.
We're in a-
Yeah, because the third vibration.
Yeah, so the first one is out and it starts to go up. Even though the most probable position is in the middle.
I was gonna say.
No, it's independent of energy. And momentum is average momentum is so it would be, I only remember that because I've been teaching, helping someone with this.
Thank you for coming, and without being ironic, thank you to those who come a little late. I'm feeling myself a little better. So how is your mood and energy?
It's raining outside. I wish it was snowing. Just think how much snow we would have.
That's fine.
Is it expected to be extraordinary?
Shortly.
It would be great. We would have like 3 feet of snow.
How do you know?
An inch of rain.
We haven't got 3 inches of rain.
What do we do?
Weird comments.
No, yes. But what we have just 3 meetings left. I had an initiative from some attendees of the class to make the presentations later, but I think not everyone will support this idea because some of us will travel. So next Tuesday is the last time when we can meet as a whole group. So if you feel that it is too much stress to prepare presentations by next Tuesday, you should get a self-reward that you are making an act of self-sacrifice for your comrades, classmates, who cannot attend at the other time. Okay, so I do understand that it is a very big stress to complete projects in the remaining time. Actually, the calculations, the project should be complete by now. In the remaining time, there is only the opportunity to wrap them up and prepare the written reports and presentations. So do not hesitate, do not be perfectionists. Even if something is a little below your personal standards, everyone understands that it is an academic course. You cannot do perfect. And same as like, if you have experience of submitting academic peer review papers, you know that typically they do not have deadlines because high quality research cannot be done by a certain deadline. So it is a little excuse for being practical rather than perfect. So there are 2 critical things to complete. 1, written reports, which you have 2 nights to complete. So you just throw in whatever you can tell about your projects in a couple of pages. Do not be long. Do not think that it is so important that I will write 100 pages report. No. Be brief. Just main statements. What you have found, like what is the scientific challenge, why you selected this problem, what you were doing, a couple of main images, figures, and conclusions. Like extended abstract or very shortened seed of a paper. One of intentions to leave short time for this writing so that you do not get it too long and I do not have to read long write-ups. And the second challenge is to, I may forget it, but let me focus on it right now. Please bring your write-ups to the class in the printed form in 3 copies. Do not email it. Well, you can email it to me, but I will still ask you to print them. So come in 2 days to this class with 3 printed copies. Okay? Good. Challenge number 2 is to squeeze each project into 3 minutes presentation, which is probably even more challenging. And we will make these presentations in literally 1 week from now, next Tuesday. And after we have many restrictions. Some of us are traveling outside of the country next day. Some of us have next class exam in 15 minutes after these presentations are complete. So there are limitations and we need to be in limited time. And if there will be, you're welcome to bring your, invite your guests to see your minute of glory. But I will remind to those guests that any questions are very welcome, but no more than 2 minutes per questions and answer section. So even if someone will ask and will come up and tell, I want to oppose what was presented, I will cut and not allow people to criticize you too long. Because there are objective difficulties in matching the limited time period. So these 2 types of activities are replacements of the standard exams. So they are main criterion towards grade and success of the course. And we are going this way with understanding that all of you are supportive for this idea, rather than making written assignments, sitting and doing standardized problem solving or practicing your memory and memorizing some definitions or whatever. Am I right? Okay. So, written reports and presentations. The rest is decoration. So if you know how and when and if you're sure that you will complete it, you can lean back and relax and I will entertain you with the remainder of the time. So today we will cover, it will be last portion of pure academic material. If we miss something today, then we miss it for the whole course. But I think by now it's already a very good progress and you have a core, well, from what I see through the quizzes, feedbacks and your performance in projects, there is a very strong core of background knowledge and skills. So you shouldn't worry about your awareness and development as independent computational chemistry researchers. What you have is already enough. We just polishing and adding a little bit from each side. So today we will complete the time-dependent density functional theory section, and if it is not sufficient, I think there will be another course. There will be another course next semester which will be a little more detailed, theoretical, and when one can go to less practical, more theoretical backgrounds. It's like opportunity if you want to go to larger details. So we will complete the 4th chapter with flowchart for time-dependent density functional theory as a tool to compute spectra, and it will be more than enough for your independent journey on a sea of computational research. The rest of skills can be picked up as one goes. There are this sound typically comes when recording goes off record, but it is not. It's okay. So before we go to academic part, I will provide a couple of comments about your completion of research, writing reports, and you do not need to take notes. It will be more entertaining part. So it will be much less intellectually challenging. And before we go to these two sections, completion of TDDFT and overview of scientific communications, I will distribute a couple of handouts that which are very optional. You are free to consider them as a kindling material if you are not curious about the stuff. It's supplemental. So this is one of the textbooks that covers time-dependent density functional theory. And if TDDFT is workhorse number 2 for research, and a lot of practical research papers are done with the theory, but it is a little younger than density functional theory, and it is not included in some of the textbooks. So if you take a general textbook or earlier editions of the books, you will not see, or you will see just mentioned in the form of text rather than derivations. So this one is more overview book rather than a text, but it has enough of necessary words, and it shows main equation that is being solved while one is getting this transition densities, excitation energies that we were discussing last time. Okay. Another handout is a little summary. So if you would, typically when you write a scientific paper of applied character, you do not go into much details into methods. You just mention this software with this method, and if you want to be very rigorous, you can mention a couple of basic equations. So this chart is an extraction of a little more than minimal amount of equations for this theory. More for following the context notations. What else do I have? Who likes quizzes? No? Me too. You may use it just for your entertainment. But again, remember, all academic activities that we are doing right now is supplemental. Our main goals are projects. And I have one more, which is not scientific and academic. It is more practical about the written reports. So, do we need more labs? it is right now, there are no critical necessity for the labs, but some of you may want just to use assigned time as a help section or interaction. So I plan to be in the computer lab tomorrow from 5 to whatever it is needed, Wednesday night. And if there will be necessity, if I see from individual feedbacks, I can be also in this lab on night before the presentations, just in case someone feels that last final touch is needed. Okay. So here is an overview. It's just more for my members, what you are doing. So we do have set of projects. So some of them dealing with minerals and crystals. Some of them are dealing with metal-organic catalysts. There are works on metal clusters for either catalysis or bioimaging, labeling. Well, it is another question that you may want to answer to yourself in writing reports. Even though motivation of a true scientist is just curiosity, since scientists are not isolated, they interact with society, it is always a good tone to start and end your write-ups with motivation and impact. Like, who needs whatever I'm doing? What are possible applications? Who else will benefit from these results? And just keep thinking of it while writing. So there will be a couple of presentations on nanotubes usage for sensors of gas, so electronic nodes. Several presentations of metal interfacing of organic and inorganic interfaces. Metal to semiconductor, semiconductor to organic, and metal to organic for different variety of applications. So just 3 meetings left today, Tuesday. Today is Thursday and Tuesday, and we are going to not academic. Preparing your written reports. Suppose that you have completed your research and you want to write it up. We all are in the limits of time and number of pages. We cannot go too far. So very brief, like a couple of sentences on each subject, on each aspect. No more than 2 references if you plan to add references. You are generating, maybe by now, especially if you are considering reaction dynamics, you may generate snapshot of each time step. Like you may. It doesn't mean that you need. And it doesn't mean that you need to include it into your write-up. So you have a internal challenge of selecting best figures and combining them, because you cannot put 200 figures into 2 pages. You need to select the best ones, most representative, that communicate main message. And no one in the world except you know what your main message is. Other people can just guess. Most of the times wrongly. So you need to guide a silly reader, like, I want to study this one, I'm doing it by this way, here I repeat my main message, here is the main result. Please look on it and appreciate how big impact it has. So reader is like a baby. Do not hesitate to repeat some basic things. So one of the basic things, who needs research? Right now in the papers, it is not as important, but in the important aspect of academic life, the application for federal funding, it is a critical thing. So you do not need to do such silly pictures like this one. It is only for an idea that scientist is not isolated. It's not a spherical scientist in a vacuum. It is interaction with other scientists. It is interaction with taxpayers, and it is benefits to industry, somewhere medicine should be, like health. So whatever we do can be converted into form of either publications of patents that go to the industry that generates some fancy stuff for end user, like give it more energy for cheaper, give it like comfort, pharmacy, also some education, because also the byproduct of scientific activity is generating of workforce, either who do practical research or to those who pass knowledge further. And then we are pulling money through government, we are pulling money from taxpayers. But one may want to tell which practical benefit your research gives to the society. Like photovoltaics, free energy, or if the oil prices are not high, catalysts that help processing oil products with better efficiency, or maybe, well, too long story, and each story is very personal for each individual project. You all are developed, grown-up adults. You were going to school, you know how to write compositions, essays, and I'm a bad writer. I do not know how to write good, but there are some tricks, there are some specific steps that help to complete write-up in a readable, organized way if you identify plan and some sections. Most of you know it by heart, but just in case, we can go through it. So, in today's technical writing, especially for short papers, typically one breaks each write-up onto sections: introduction, methodology, results, and conclusions. And sometimes one adds abstract and whatever. So, if a reader or reviewer reads through paper in a rush, one is looking for keywords to identify the sections. So if you do not want to surprise your reader in a bad sense, you may want to include the sections. Just mark them: introduction, methods, results, conclusions. Sometimes one takes results and discussion or adds discussions additional section. So what you may want to write there. So here is very oversimplified. So what are you looking at? What is an open problem in this area of research that you are looking at? And you may guess a hypothetical answer to this open problem. No one tells that you need to guess it before the research. You may complete the research and then just wrap up your introduction in such a way that you already know what your answer is, but you tell, let's check whether this answer will be right or wrong. It helps reader to go through the description much easier. And then you tell, I do not know if it's correct or wrong, but my experiment or computation or some theorems may help to answer this question. So, like, 4 sentences is more than enough. Do not be for methods. Why does one need methods? If we all are sitting in the same class, we share the same skills, well, maybe some of the readers will be not from this class. And maybe we want to make sure that the reader can reproduce the results. So some very basic information. which software, which functionals, what are the notations if you do some fancy observables. And I'm willing to share a template for the method section if you want. Just send me an email and I'll share. And our main goal is not write this one because we all are on the same boat and we know what they are. So I should do it like by tonight at latest. So main challenge, results and discussion. So you identify among your tens or hundreds of figures or figures that you can imagine, most important, that support your hypothetical answer to your question. Only illustrative. And do not worry if you are not showing, some of you are worrying that you didn't match all your plans and didn't make 1,000 job runs. And some of you may worry that, oh, I have this, this, and this. How can I speak about this aspect if I'm not showing the figure? It's normal. You can see that reaction goes downhill according to obtained results, and in brackets, not shown. You cannot do it with everything, but you can take out 90% and show mostly representative examples. It's life. We cannot show everything. If you want to be meticulous, you can send hundreds of figures into supplemental material, but not in the main document. And as a minimal result, if you are short in time, if you do not want to do, what is the heart, what is the core of this report? A couple of figures and figure captions. Like, oh, on this picture I see this. This looks this way because la la la. So it is a minimum, and the rest can be wrapped around. So if you do not know where to start with selecting figures and explaining them. Here, we'll go to, no. And when you go to conclusions, you need to make a feedback loop to your introduction. Tell like, okay guys, you followed my write-up, you saw these results, and now you see that the answer is most definitive, that hypothesis was correct. Hurrah. It will be used to save the planet and make everyone happy. Done. It's fine. So you convince reader that what you found is readable and trustable. Here, probably it is not shown in slides. There is last handout for today. Maybe it is the most valuable one. So it is so nothing is mandatory. You are creators of your content. So it is just a little prompt of what to do if you have no ideas, or if you didn't have enough coffee, or if you didn't sleep enough, and you need just a little crystallization center for your ideas. So you can characterize geometry, characterize basic electronic structure, tell that I perturb to explore properties of system, I perturb it by whatever, light, heat, electric field, and here are properties of the system after this perturbation. If initial and final are not sufficient, then you can include some intermediates. If it is reaction dynamics, you may compute total energy at each step and tell, like, here I estimate the barrier of the reaction. There are no literal guides, step-by-step guides to research and papers, but there are some general ideas. Okay. Why this picture is here? Any ideas? Because a scientist is not a spherical scientist in a vacuum. Because we cannot do things just to satisfy our own curiosity. It is always, even if you satisfy our own curiosity, we need to talk to other scientists and make them to believe that we are going in the right way. We need to talk to sponsoring agent. So there is a way, and most important, if you look from cynical point of view, scientists need to interact with editors and reviewers, because the criterion, first criterion of success is acceptance of papers, and it is done by humans, not by robots. So you discuss with, you argue with the reviewer that you are doing the right thing. Or you as a reviewer, you argue with the author telling like, it is very suspicious, you need to redo everything. The idea that one needs to argue with reviewers is not new. Although there was not modern science in our today's understanding in ancient times, the idea of arguing was very popular for a long period of time. And the way how to arrange scientific communications, or generally communications, in order to convince people to do or not to do something, is as old as the civilization. And some people were living the instructions how to do it, some of which are not very bad and can inspire us to write better or speak better. I don't know if it is always possible, but at least we can be aware of this. So two people. One is Aristotle, philosopher, who was telling like, okay, if you're going to speak in public, you need to know what you're speaking about, you need to organize your stuff, and as the last thing, you need to memorize it and think how you present it, which is self-evident. And it looks more on the reflecting what is going on. The representative of another part of ancient civilization, the Roman, so Aristotle was Greek, and representative of the Roman civilization, they were more practical, more to engineering rather than science, and to they were looking more on the practical aspects of human life and to practical aspects of the communications. So one of the most famous speaker of this stuff was a person with name Cicero, and he mentioned that there are three goals of any presentation: is to teach, entertain, and induce people to do some specific things. So if there is no entertaining component, then people will not listen to you. If there is no teaching, if people do not learn something new, it also will be boring. And for your own sake, you start speaking because you want people to do something. Again, it's not my idea. It's just borrowed from what people were doing in ancient Rome. So there is we did have a list of the sections for modern papers: introduction, methods, results, conclusions. The communicators of ancient times also were splitting presentations onto sections. And this is just from Wikipedia, but I think it is big fun. So the splitting of material on the sections was very different from what we do in the following aspect. We today, not we, everyone in our civilization, at our level of civilization, mostly people look on the technical part. Like introduction, 10%, methods, maybe 20%, results, 60%, conclusions, 10%. If you do not have results, why to speak? these proportions were upside down in the ancient time. Maybe they didn't have computers to generate many results. But the results, or what was analog of results, was about 10% of the communications. The rest was to motivate people to listen to you and convince people that you are correct. So mostly to the discussion. And here are some fancy ancient words for this section. So there were 6 instead of 4, and it was a little different partition of the effort towards the final document. So introduction, or maybe abstract exordium, where you urge and tell, like, let's go and look at this because it is really important. Then narratio is more like literature review, what other people are doing and how it was addressed before. Then it was really big portions. Then you summarize what you are going to do in the rest of the document. Right now, we have a little traces of this activity, which they call divisio or partitio. At the end of the introduction section, many papers have, our paper is organized as follows. And then tell, like, or if it is a long review paper, there is a table of contents. Here it was more in the ancient times, explaining what is the structure of the document. And then there was very short, very brief confirmatio, the proof of the main statement. Where if it is math, it is a proof of theorem. If it was more natural science, is explanation of what one can do. I have no idea how it would project to medicine or law, but some proof. And then 50% of the rest was actually discussion. So imagining how the audience and reviewers may criticize what you are offering and offering counter arguments against possible criticism. So this was main part of ancient communications. And in the conclusion, you repeat everything what is important and then summarize the argument, blame anyone who is not agreeing with you, and it's again not my words but from the Wikipedia about the rhetoric. Arouse sympathy to the author, client, or the case. So you may plan on doing this in your written reports or presentations, especially if you will invite some guests to witness your minute of glory. So we already went through this. So some of you are looking on the material before and after perturbation and compare their characteristics. Here is what you already got as the handout. So tables and figures. This is maximalistic. You will not survive if you try to do 7 figures. No. This is a wrong number. 2 figures at most. You may squeeze a lot of materials in a figure by doing multi-panel. But design them. Do like 4-panel figure and do longer captions. But if you do just single image and do 10 figures, you will not be in the format and you'll waste your time, and it's not what we can do in limited time. You know, you don't need to be perfect in the quality of figures as by now. You can improve them later if it is a seed for your big life papers. You can take the images and just glue them together in PowerPoint and then capture screen as one figure. Or some of you are proficient with Origin and can do it. Or if we are generating this with GNU-plot, these PDF images, one can catch and place them in the PowerPoint and make one multi-panel figure. But do whatever is quicker for you. The time frame doesn't give us opportunity for perfectionism. Get to the main point as quick as you can. we are past this point. So we have a little time to go through time-dependent density functional theory. So when we met last time, we have discussed that any theory for excited states has two purposes: compute transition energies and compute oscillator strengths. Right? And we went through the way how they are computed, either through in orbital picture or in transition density matrix picture with help of trace operation. Good. When we will meet tomorrow night, our main goal will be, my goal will be to assist you to complete the projects. But if someone will be like, everything is done, I'm bored, I'm just yelling and looking what else, I will be briefly showing how to run time-dependent density functional theory calculations, which is same as you did in Gaussian for density of states, for ground state, with just very little changes in one line. And today I will briefly come over the output that is generated by TDDFT calculations in Gaussian. Other thing, if time allows, I may show the calculations of normal modes for molecules. But again, this is for people hungry for additional knowledge. Excuse me. For projects, we have everything is necessary. So you add keyword TD and you type root number of excited states. That's it for TD DFT calculations. And excuse me, you may want to start in the same directory, and you may want to start in the directory where you do have check file from ground state calculations. So this TDDFT calculation can pick up information from there. So like orbitals and ground state density, and build TDDFT on the top of this. So after this calculation is complete, we are going back to Gaussian. There is a generated .log file that has in text format everything which is needed. So, and at the end of the file, there will be a list of excited states. Again, in our orbital pictures that we are doing for projects, each excited state is a pair of orbitals. One orbital to another orbital. In TDDFT, the excited state is a superposition of several occupied and several unoccupied orbitals. Some of these superpositions may be reduced to pair of orbitals, but it is not always. So some excitations can be still pairs of orbitals, but many of those are several occupied and several unoccupied, contributing to one excitation. So the .log file has a format of keyword excited state number, and then it shows the transition energy, oscillator strengths, so basically two things that we need. And then additional information, pairs of orbitals involved in this excitation, and percentage, how much of this transition between two elementary orbitals contributes to the excitation. If there are some additional orbitals that contributes at a vanishing level, they are not listed. So for this specific model that we will probably consider tomorrow, titanium hydroxide, and you are doing it years ago, well, 2 months ago in homeworks. HOMO is 24, LUMO is 25, so it is elementary excitation. But the next excitation is a superposition from HOMO -1 to LUMO and HOMO -1 to LUMO +1. And they are coming, well, it is not transition these proportions can take negative parts because they have phase factor. So there is an excitation energy which is bigger, so it is next one. There is a oscillator strength, and there is this contribution of elementary pairs to the excitation. So how does it relate to whatever we were discussing on previous meetings? So these proportions of individual orbitals contributing to excitation are related to transition density metrics. So basically they are those elements. And if we are looking for the lowest excitation, then you see from here that only this transition density matrix element from HOMO to LUMO will be non-zero. The rest will be either zero or vanishing. For practical reasons, we do not need to look below this line. If you have transition energy and oscillator strengths, we can go directly to computing of absorption spectrum and be happy. This is just if you want to see a little bit more of what is going on. So, for ground state, we have only diagonal below HOMO occupied, and for transition, we have this HOMO to LUMO non-zero. And since we are in the lowest order of perturbation theory, we will never populate the actual excited state elements of density matrix. If we are looking to the next excitation, you see that here is from HOMO -1 to LUMO and from HOMO -1 to LUMO +1. So these two elements of transition density matrix will be non-zero, and the rest zero. And so forth, one continues the exploration of all excited states. So this element this much, this element this much. So basically, TDDFT calculations provides values of transition density matrix elements. And then one can pull transition energies and oscillator strengths and build absorption spectra, which between 3 and 4 electron volts. So transition energies matches what is expected for titanium dioxide. We can look how far it will be from what we got as the HOMO-LUMO gap in ground state. In this case, it will be not very far. But in some organic molecules, TDDFT is much more reliable and helpful. So we need to have it in our arsenal. So which equations are being solved? So this is the Canadian scientist who is very proud of his ability to speak French, as you see here. And he is generally is happy for this equation. So Mark Casida has derived, the idea of linear response and for converting time-dependent Schrödinger equation and time-dependent Kohn-Sham equations into frequency domain were made before him, but he has formulated it in a closed form for well-developed equations for transition density matrix and frequency. So it is same thing that you have as a handouts, and you may see in papers or scientific presentations this equation, but sometimes it looks a little off. I was staring on it for a couple of years at the conferences before trying to think what it is. So why minus is here, -1? Because those are for excitations and for emissions. So those are different transitions with loss of energy and gain of energy. Therefore, they contribute with different signs. So this is eigenvalue equation, and those x and y elements are transition density metrics, namely coefficients in front of pairs of orbitals showing how they contribute to the density. And the coefficients of the supermatrix that we are diagonalizing, in the zeroth approximation, those are just energy differences between basic quantum orbitals, and in the complete version, it is second derivative of the total energy over the density, or first derivative of the potential over the density. So it is included into, it can be included into self-consistent DFT procedure, where one computes density, derivatives, makes diagonalizes equation, and then repeats it iteratively. So another thing that may look a little off and challenging, we are talking about matrices. Density matrix, transition density matrix, and eigenvalue equation is formulated for vectors. So what is the connection between these matrices and vectors? The transition density matrix can be written in form of a vector if you just take each element and record them one by one. And then indices in the supermatrix can be also arranged. Although there are generally 4 indices, one can block them in pairs and then form vector in form of these elements of matrix and super operator in forms of this objects with pairs of indices. And then it looks in the same way as in typical eigenvalue equation, matrix by a vector. Find eigenvalue. So if someone wants to program it, one may want to make a flowchart with input, output, mathematical operation, and conditions. So when we start TDDFT calculation, we, as in any electronic structure calculation, we start with position of each ion, number of electrons, tolerance limit, and number of requested number of excited states. As an output, our primary output is transition energies and oscillator strengths, and as technical byproduct are transition densities. And we need to form total density, and we need to solve this eigenvalue equation for the densities, for transition densities and transition energies. Let's try to throw in all this data into a flowchart. I will try to do it myself on the board, otherwise it will be a little boring. As output, we need transition energies, oscillator strengths, and also this density matrix, X and Y, transition density matrix. If we are looking from backwards, just before we go to the output, we need to compute the oscillator strengths and transition dipole. as trace of this x transition density matrix times dipole operator, because we are in the dipole approximation of light to matter interaction. Some people may consider it's confusing. It's and then one goes to oscillator strengths, and then to the power. One starts with positions, tolerance limit, and what else do we need? Background. And, generally, it is not required, but well, the code is intellectual enough. If you do not provide ground state calculations in the same directory, it will perform it by definition. But actual TDDFT starts after ground state is completed. So we may also have the orbitals, the ground state orbitals, and ground state density. What else I missed? The number of excited states. So this procedure is more expensive than ground state calculations, and the larger the number of excitations you need, the longer it takes. So it is very wise to specify it. And since the code is intellectual enough, if you do not specify it, you put it to a really small number, like 3. Well, you may need 100. And it is referred with the keyword root. So then one needs a guess for transition density, because it will be again self-consistent procedure. And then, as if you do through self-consistent procedure, on the next steps, the density will be provided through the cycle. And then, after we do have transition density, we can compute. Total density, ground state plus summation of this x. So we can generate total density and total energy as a function of the total density. Then one needs the coefficients for the Casida equation.
Question: when you times y, IA, why do you not have a constant?
I do. And there are more precise and detailed equations, but basically these coefficients are second derivative of total energy to the functional derivative to the change of density. It's their meaning. So calculations of the supermatrix. And then one formulates the Casida equation. So these symbols x and y, they represent block of data. It's not one number. It's like a column of 100. So instead of putting this matrix with -1 in front of in here, one can just put minus in this matrix. This notation. So then criterion of convergence is energy, transition energy of a specific excitation. So we need to select our favorite number I and check old and new excitation energy for the same transition. So if it didn't converge, then we need to repeat the whole procedure. If it does converge, and our state that we are using as convergence criterion is a lower excitation than those. If you didn't go through all needed excitations, then we need to look through next excitation energy. So if we already came to the analysis of excitation that is needed at our original request, then we can go to computation of observables. If it is no, we are coming to the next excitation and use it as a criterion for optimization.
Isn't yes and no backwards?
Yes. And through several steps, one is optimizing transition density and transition energies. And then one computes oscillator strengths and get to the ability to compute absorption strength. Let's check how far it is from what was pre-recorded. So going to next iteration, and here is block of 3 calculations with getting the density, computing this supermatrix, formulating the Casida equation, the match of the tolerance limit, going through all needed excitations, and then computing observables. Academic part of the computational chemistry course is done. What one can do in half a year. So we did have 4 chapters. First chapter was molecular Hamiltonian general and separation of electronic and nuclear degrees of freedom. Then we had a big chapter for Hartree-Fock theory, which is not as useful for today, but it is important academic achievement of the civilization as a step towards next theories. Then Brown state density functional theory, which is a workhorse for most of calculations. And recently we have completed time-dependent density functional theory for trustable analysis of excited states. So by completing the course, we all are expected, and I have no doubts that we have practical skills of building models, optimizing geometry, characterizing electronic structures through density of states, electron affinity, and ionization energies, being able to compute absorption spectra, characterizing the reaction dynamics, reactions through molecular dynamics, and analyzing this reaction dynamics through movies. There are additional auxiliary skills that can be helpful, but this provides sufficient core to do research and use the skills as a complementary tool to your experimental research. So you do not need to be dedicated theoretical chemist or computational chemist to use these tools in your research. You are approaching the state of art skills, and you should be able to do like independent papers, single author papers with some computational skills, or maybe with some of your primary group members. So the meeting is done. I will stay here to answer questions, if any, and everyone is invited to visit the labs on Wednesday night. What do I owe? I owe the one paragraph on methods. Is that please? If you do not see it, I would appreciate a reminder.
So you